Good morning, all of you. And it's a rare occasion to take a really challenging problem as well as logically consistent and decent. And if you have not subscribed to the channel, please do it because I'll come with more quality content for you in the upcoming lectures. So this problem teaches you many things. One is how to comprehend the problem. Second is how to use your comprehension to draw the proper diagram. And third is once you have drawn the proper diagram, how to model the situation nicely. And that's the major ideas behind most of the undergraduate tests, especially Indian examinations. So let S minus be semicircular arc defined by x plus 1 whole square plus y minus 3 whole square equals 1 by 4 and x is less than equal to minus 1. S plus b semicircular arc defined by this equation. R be the locus of point P such that P is the intersection of two lines, one of the form x plus by equals 1 and other is of form cx plus dy equals 1, where cd is from set S plus and AB is from set S minus. What is the area of R? Now before you go further, it's better you pause the video and try to solve this question by your own. That will enhance your comprehensive ability. Not only this problem is useful for JEE, but also it very beautifully tells you how to approach a new problem in the examination. Okay, so first I'm going to give you the feel for the problem. So as such, we'll draw the semicircular arc, which is defined by the first expression, and it's not very difficult over here because you can clearly see this is arc having center minus 1 comma 3 by 2, and we have radius as half. Okay, so we'll have center over here minus 1 comma 3 by 2, radius half. So the lowermost point is going to be minus 1 comma 1 and the uppermost point is minus 1 comma 2. Similarly, so this region, this part I am calling it S minus. Now S plus is this semicircular arc, and again center is 3 over 2 comma 1, as you can see. So x coordinate is 1 and y coordinate is 3 over 2. So it's 1 comma 3 over 2, and the maximum height, since radius is half, so this point is going to be 1 comma 2 by symmetricity and 1 comma 1. Okay, I've drawn a lot of diagram so that we can get the feel of the problem. So I hope this is clear, right? Okay, so let's move ahead. Now, what does problem tells? R be the locus of a point P such that, what is point P? It is got by intersection of two lines, one of the format ax plus by equal to 1, where AB belongs to S minus, and other of the format cx plus dy equals 1, where CD belongs to S plus. Oh, that's cool. It means, let's say if I take this point, right? So this is member from S minus. So it means I can take the equation of a line cx plus dy equal to 1. Okay, so here C value is where CD belongs to S plus and ax plus by where AB belongs to S minus. So here I have taken A to be minus 1 and B equals 1. Okay, because any point A comma B is the ordered pair which is belonging to the set S minus. So I can tell basically S minus is a set of all xy such that this relation holds, right? Similarly, S plus is a set of all xy ordered pair such that this holds. It means any point will satisfy this relation. So to comprehend the problem, what I am doing is to take a particular point. So let's say from S minus, I am taking a point A comma B ordered pair. Corresponding to this, I am creating a line. So how we have to create the line according to this mechanism? Minus x plus y equal to 1. Right? So here you can see the x coordinate, x intercept will be minus 1 and y intercept will be 1. So I'll have a line like this. So this is line number 1, which is obtained by creating from ordered pair from S minus. Similarly, let's take a point CD which is belonging to S plus. So for the sake of simplicity, let's take this point over here. Okay, and now if I'll put C comma D over there in this expression, so I'll get an equation x plus y equal to 1, and x plus y equals 1 will look like a line. So let me draw like that. X intercept 1 and y intercept 1. So clearly it's a line x plus y equal to. Now these two lines intersect at a point P. So let's call this point as P. Okay, so I've given just example of 2 points. Now we can repeat the process for infinitely many points. For instance, let's suppose if I take this point minus 1 comma 2. Right, so corresponding to this, the equation of line will be minus x plus 2y equals 1. It means x intercept is minus 1 and the y intercept is going to be half. So the line will get something like this, right? So this is corresponding to minus x plus 2y equal to 1. Similarly, let's take, if I take 1 comma 1 from C, the same line. So these two lines intersect at this point here. So that is a new location of P, right? Again, let's suppose if I take this point, so corresponding to this I will have some line. If I take randomly this point, we'll have some other lines. So if this ordered pair is A comma B and let's say C comma D, so this will represent any two random lines and that will represent on point P. So point P will be infinitely many points here in the plane. Okay, so it will bond some area. We need to find the area bonded by all set of points P such that AB comes from the left arc and CD comes from right arc. So having understood the problem, let me take a situation. Suppose if I take a random point A comma B on the left arc and C comma D on the right arc. Right? Now under this configuration, what I'm going to do is, let's say A comma B corresponds to a line, right? A comma B corresponds to a line, and that line can be anything because let's say that represents a line and whose equation is given by ax plus by equal to 1. Similarly, corresponding to C comma D, I can generate an equation cx plus dy equals 1, where cx plus dy equal to 1 will represent some line over here. And let's say the point of intersection of these two lines, cx plus dy equals 1 and ax plus by equals 1, be alpha comma beta. So since alpha comma beta is the point of intersection of both lines, it must satisfy both. So we'll have a alpha plus b beta equals 1, and similarly c alpha plus d beta equals 1. Now this is an interesting result because this shows if I consider an expression, let's say alpha x plus beta y. Okay, so alpha x plus beta y becomes 1 if I insert point a comma b here, because a comma b will make this 1. Similarly, alpha x plus beta y becomes 1 if I put an ordered pair of real numbers c comma d here. It shows now alpha x plus beta y equals 1 is the equation of line, and this line is passing through 2 points a comma b and c comma d, and that 2 points is clearly here in the curve. So I know if the point of intersection of the corresponding line with respect to A, B and C D is alpha comma beta, we got a very interesting result, and the result is alpha comma beta is a number, let's say 2 comma 3 or something, let's say 2 by 3 comma 1 by 3. So corresponding to that, if I'll make a line equation with those as coefficient, which is 2 by 3x plus 1 by 3 y equal to 1, that will easily pass through the point A, B and C D. Okay, so that is very exciting because alpha x plus beta y equal to 1 is a line which will definitely pass through A, B and C D. Now what is great about this is this conclusion. So here is my claim. If I take any 2 points on this line, the line containing A, B and C D, let's take another point I'm taking as PQ and some random point as R and S, right? And suppose corresponding to PQ, so let me again redraw a diagram over here. That's why I've kept so many diagrams. So till now what we have seen, we have point AB and CD, and the corresponding line created by AB and CD intersects as a point alpha comma beta. And now I'm going further. So suppose if I have two more points, some P comma Q and R comma S, which is lying on the line containing A, B and C, D. My claim is, if again I create a line Px plus Qy equal to 1 and Rx plus, inserting these coefficients if I create some line. So again it will represent some random two lines in the plane, right? So corresponding to PQ, it will represent some line. Okay. And similarly corresponding to RS, it will represent some line. Now my claim is, even these two lines intersection point will also be alpha and beta. And that's really great claim. So let me first prove the claim. This a small part can itself be a problem of J advanced, right? Because it has nothing special in its theory, it's just conceptually loaded. So now my claim is, if I take any point PQ and RS with those real numbers over here, the ordered pair of real numbers associated with this. When I'm talking about point PQ, means basically I'm taking point like 1, 2, 3, 4. So it's basically P and Q are real numbers. Right, remember I'm taking all these are R2. In that sense I'm talking about. So let's prove the claim. Since we know Px plus Qy equal to 1 and Rx plus Sy equal to 1, we have to prove like even the line of intersection of these both curve is passing through alpha comma beta. Since we know P comma Q lies on the line given by alpha x plus beta y equals 1. So P and Q will satisfy this, hence we'll have P alpha, plus Q beta will be 1. Similarly, we'll have R alpha plus S beta equals 1. Right? And now you try to feel this situation. Now of course we'll have Px plus Qy equal to 1 is some line corresponding to the point PQ, right? Randomly somewhere, let's say this is Px plus Qy equal to 1. This line is Px plus Qy equals 1. Corresponding to Rs, I can clearly generate a point Rx plus Sy equal to 1. It may meet, may not meet, but here the existence of meeting point is guaranteed. That's what I am showing from here. Okay, now Px plus Qy equal to 1 have a point alpha comma beta on it, because this equation is satisfied. So I can tell alpha comma beta will satisfy this equation. Similarly, if I have Rx plus Sy equal to 1, this will represent some arbitrary line over here, right? It also contains a point alpha comma beta, because from this relation I can tell alpha comma beta on this line. Now I know both of these equation is equation of line and there is a common point alpha comma beta on them, right? Hence they must intersect on alpha comma beta guaranteedly. And that's surprising. It means it shows if P comma Q is some line, it should also pass through alpha comma beta. Similarly, if R comma S corresponding to this, if I create an equation Rx plus Sy, it must pass through alpha comma beta. So if I'll take any point here, let's say again some Tu corresponding to this, if I create a line, it will again be concurrent. So you keep on changing points on this line, and for each and every point treated as an real numbers, its corresponding image in the line world is going to be concurrent, and that concurrency point will be alpha comma beta. And that's really surprising result, right? That's really exciting. So here I'm going to use that result to move further, and here we go. So now my claim is, let's say if I take any 2 points A, B, C, D over here, and suppose their point of intersection is some alpha comma beta. So now what I'm claiming is, since if I pick up any points, any 2 points on this line, their point of intersection is invariant, it's still going to be alpha comma beta. So now smartly I will take 2 points as the point where the line containing AB and CD intersects the horizontal line x equal to -1 and x equal to 1, let's say at these 2 points, right? And I can call this point as -1 comma some p, and that point is 1 comma k. So again I'm repeating, what I'll be doing now is since minus 1 comma p and 1 comma q will have same point of intersection alpha beta as the point a comma b c comma d. So now instead of making two variables c d and a b, in fact we have four variable here, right? C changing, d changing, a and b can change. So now I can replace the problem equivalently to just two variables. Why? Because you give me any line, I can always take 2 points here, minus 1 comma p and 1 comma q here, such that the point of intersection corresponding to this line, so minus 1 comma p will create some line, 1 comma q will now create some line according to the rule. According to which rule? So now I'll create x plus qy equal to 1, so that will be given this line, and minus x plus py equal to 1 will come in. So both line will still intersect at alpha comma beta, right? So because of that intersection, now what I'm take advantage is, now I can forget this entire curve and I can replace this entire equation just with these two vertical bars. Why? Because let's say now if I consider any 2 points, 1 point over here and 1 here, so corresponding to this always there exists 2 points now. So let's say if this point is some Golu and Bolu, so now we have Vicky and Ricky over here, which will take care of all that. So corresponding to Golu Bolu, I was creating two lines which was intersecting at let's say alpha beta. Now corresponding to Vicky and Ricky, definitely both lines if I'll create simultaneously by plugging the real numbers, ordered pair as the coefficient of x and y, I'll get same intersection. So now what I can do is I can forget this branch, right? And now just I'll be concentrated only on these two vertical bars. So hence the equivalent problem is now just we will consider these two vertical bars, and corresponding to this I'll take any point, let's say minus 1 comma some r, and here I'll take 1 comma some s. Okay, and then I'll write minus 1 comma r will give an equation minus x plus ry equal to 1. 1 comma x corresponding to this I'll create an equation x comma sy equal to 1, and I will solve both of these lines. So if we'll solve this line, let's say we'll get a point of intersection over here. And what is point of intersection? That's not very difficult to feel, because we can simply add this equation and we'll get r plus s times y equal to 1. So hence y coordinate of point of intersection is 1 by r plus s. And if I'll plug this in the x coordinate, right, so if I plug this in the x coordinate, what I'm going to get? It will be 2. 1 plus 1 is 2. So y coordinate is 2 by r plus x. Plugging the value of x that I am getting is, can we check once? So it will be r minus s by r plus s. So hence the coordinate of the point of intersection in the transformed world is r minus s. In fact, it's not transformation, it's a smart world, is 2 by r plus s. Now equipped with this idea, I'm ready to finally hit this question, because now I have a vertical bar having a random coordinate where I have only 1 degree of freedom, right? And this lower point is, remember, is minus 1 comma 1 to minus 1 comma 2. We have 1 comma 1 to 1 comma 2 over here, right? And we have the point of intersection. So you take any arbitrary point here on this line and any arbitrary point there, the point of intersection will be r minus s, r plus s. And now basically we need to find the locus of this coordinate, this area bounded by this. But the problem here is r is, again, it's varying. So r belongs to 1 to 2 as well as s also belongs to 1 to 2. So basically I can see here the ordered pair r comma s belongs to the Cartesian product 1 2 cross 1 2, right? Well, so far so good. Now it's not very difficult because we'll play with certain values. So let's say if I fix the lowermost point, so if I fix the value of s as 1, and let's say ra if I fix the lowermost point, right, r as 1. Remember, minus 1 1 is already fixed. So what is lying in the y coordinate, and y coordinate is basically given by r and s, because r represents this height where you are going, right? So this is the representation for r. Similarly, the height over here is representation for s, and that is sliding from this window 1 to 2, and so is from 2 to 2. Fine. Well, so finally, now what we can do is, let's take some cases. So what if I take r equals 1 and s equal to 1, then the point I'll get is 0 comma 1. So that will give me one point of intersection 0 comma 1. So what I mean to take 1 comma 1, 1 comma 1 means the equation I'm going to get is x plus y equal to 1. Minus 1 comma 1 will give x intercept minus 1, y intercept 1. So clearly you can see these two lines are intersecting at 0 comma 1. Right? So that's the field. So I'm not going to repeat this because already too much explanation is there. So we have got one point over here, right? Let me use different color. Okay, so can we get more point? Of course, yes. So I'm taking first the boundary point. So we have 1, 2, 3, 4 boundary points. The boundary point will give a boundary region, and then we can claim that each and every point within the region can be achieved. So let's take again r as 1 and s as 2, the other point. R as 1 and s as 2. So we'll get minus 1 by 3 over 2 by 3. So minus 1 over 3 comma 2 by 3 will be the point somewhere here, right? So that is the point minus 1 by 3 comma 2 over 3. Now let's take more point. Let's reverse the thing. If r is 2 and s is 1, so we'll have 1 by 3 comma 2 by 3, right? So 1 by 3 comma 2 by 3 is going to come here, exactly symmetric. What else? So what are more points that we can get out of these combinations? Okay, so what if both, if I'm taking 2 and 2, r and s both is 2 and 2, so both upper point. So r2 will give again minus x plus 2. Okay, so you see, like it will give minus x plus 2y equal to 0. So x intercept minus 1, y intercept is half. So we'll get line somewhere over here roughly, right? So minus 1.5 is this line. And similarly that will give x plus 2y. So that is also some x intercept 1 and y intercept a half. So that will intersect below the line y equal to 1 somewhere that we expect. So that is obvious. Put r and s equal to 2 each. So we'll get 0 and 2 by 2 plus 2. So 0 comma half, which I expected. So we'll have a point over here, 0 comma half. So what I got is 4 points, right? So we got 0 comma 1, 0 comma half, and minus 1 by 3 comma 2 by 3 and 2 by 3. So basically this is the region that I am getting over here. Okay, this is the region that I am getting here. And this was the area that to be found. Now the only claim which I am leaving up to you is, and which is obvious because you can just give a geometrical explanation for that, that each and every point here in this region will be achieved. Okay, for those who are watching this video, and if you want a very rigorous solution, you can make a change of coordinate. Okay, so this is left as an exercise for you. Z equals b minus d and w equal to b plus d. So this change of coordinate, okay, so in the bd plane will get transformed to a square with vertices 0, 2, 1, 3, 0, 4 and minus 1, 3. So you convert this into a new plane in b and d plane. So you will get an s square. So there you can calculate area and transform it back. Okay, so with that kind of transformation the question can be done. So that part is only for subjective examination, where you need to show the existence of all the points within as well. So finally we got area of this region. Now it's very easy to calculate the area of this region because clearly what is height. So let me take that area over here. So we have 0 comma 1, 0 comma half, minus 1 by 3 comma 2 by 3, or somewhere here, let's say. And we have the symmetric situation, 1 by 3 over 2 by 3. So what about area of this triangle? This region is nothing but area of triangle into 2. And the area of triangle is quite easy because it's half into base into height. So half into base is 1 minus half. Into height is nothing but x coordinates. X coordinate is 1 by 3. And that will give you half into 1 by 3 to 1 by 3. So it's 1 by 12. And into twice because we have 2 region over here. So into 2 is the total answer for this beautiful problem, and which gives the answer as 1 by 6. Right? Hence the final answer for this problem is 1 by 6. It was one of those challenging questions which usually is not only fun to solve but also is very excitingly gives so many ideas of problem solving. Okay. I hope you have enjoyed the lectures, because the similar argument you have also used while deriving the equation of t equal to 0 as the chord of contact. So let's say if you have a circle and if I give you a point outside the circle, let's say x square plus y square equal to 1, and if I give a point, let's say 2 comma 3, and you are asked to find the equation of the chord of contact. So let's say I draw a tangent and this point of contact is a, b. So usually how do you do? So we don't know what is point A, so we try to write x1 comma y1, and point B, suppose it is x2 comma y2. Now one way of doing this is you can write the equation of tangent, find the point A and B by solving the circle, and then write the equation A and B, and that is really the worst possible method of doing this. A smart method is at point x1 comma y1 I can write the equation of tangent, x1 plus y1 equals 1. Similarly at x2 comma y2, you know tangent equation is x2 plus y2 equals 1. And now the crazy thing is, since 2 comma 3 lies on both of these tangents, so it must satisfy both equations. Hence what I can tell is this 2x1 plus 2y1 is 1 and 2x2 plus 2y2 is 1. Now look at these two equations carefully. They fills a general version of 2x plus 2 comma 3 is there, so 2x plus 3y, 2x2 plus 3y2. So they feels as if someone has magically kept x1 comma y1 to satisfy this line, and similarly x2 comma y2 is satisfying this line. So 2x plus 3y equal to 1 represents a line for sure. Now I'm not sure whether it is line AB or somewhere else over here, or it's going to represent some line randomly in the plane, we don't know. But now I know 2x plus 3y equals 1 is a line passing through x comma y1 because it satisfies. So it can be any line still, but it also passes through x2 comma y2, so that cannot be any other line apart from the chord of contact, and hence that logic behind t equal to 0. Okay, so understanding this kind of logic is fun and very crucial, and you see a similar kind of logic has been used here when I was explaining this part of the problem. Okay, I can bet you like this kind of content as of now will not be released because you need to pay heavy price for it.